This is lesson 70, the last of the quantum mechanics and mini lecture series lessons. Quantum logic gates, so an application of quantum mechanics, one of the most fascinating ones in my opinion. So we know of classical gates, for those of us who've studied basic computing, classical gates, AND gates, NOT gates, OR gates. Quantum circuits, there are things called quantum circuits. Okay, unlike a classical circuit found in your computer or phone, a quantum circuit makes use of quantum logic gates to carry out various computations. Okay, and they use quantum particles like photons, okay, with a logic gate mathematically represented in terms of the transformation of matrices. Example, through the addition of matrices. The simplest of all quantum gates is just a quantum wire. This is called a quantum wire. Okay, which transmits an input qubit, let's say 0, from one place to another. So it takes 0 to 0. Okay, or I should say for an input state, 0. There's something called an X gate. Okay, this is the quantum equivalent of a classical NOT gate, right? NOT gate. It basically inverts an input into something else. So the X gate is like a 2x2 matrix. If you act that on state 0, let's say, if you do this, if you do matrix multiplication here, you'll get this. Okay, if we take the state 0 to be given by this column vector, and this to be 1, okay, this is what you get. So that's what an X gate does. It inverts an input. We've also got what's called a Y gate. Okay, it's represented by a 2x2 matrix as well, just like the X gate. So let's suppose we act the Y gate on an input 0. We'll get this 0i, which is just I multiplied by the state 1. Okay, it's I multiplied by the state 1. The Z gate is represented as well by a 2x2 matrix given by the following. Let's see how it acts on state 0. Oops. You get this. Okay, pretty much does nothing to the 0 state. And it's good exercise as well to find out what happens when you act all these gates upon the input state 1 as well. And in quantum mechanics, as I mentioned in the previous video, we've got the quantum equivalent of a bit, which is called a qubit, quantum bit, qubit for short. And unlike a classical bit, which can be 0 or 1, a quantum bit can be both 0 and 1 simultaneously. Because if you recall, quantum systems can exist in a superposition of states before you measure them. So in other words, a quantum bit can be represented by something like this. Okay, A and B are just coefficients, complex numbers typically. This could be an electron, for example, an electron spinning with two different spin states, spin up and spin down. It's called spin up 0, spin down 1. Okay, electrons can be used, photons, particles of light can be used as quantum bits, but a lot more useful than classical bits. Okay, they tend to be, if you were to build a quantum computer, the quantum computer wouldn't necessarily be faster than a classical computer. It wouldn't be faster, rather it would get you to your result a lot quick using the shortest algorithm. Okay, because it's able to explore more possibilities using this quantum superposition. It can take on many numbers simultaneously. Many numbers. And due to the principle of quantum superposition, you can't say that the qubit is either in either one of these two states, 0 and 1, with 100% certainty prior to carrying out a measurement on the qubit. Okay, what you get instead, as I mentioned, is a quantum superposition. And this is powerful in the sense that you can carry out multiple operations simultaneously. Let's say factoring a very large, finding the two factors for a very large number, right? You can do that much quicker than using a quantum computer, because a quantum computer can explore multiple avenues simultaneously, a lot more efficient. So I hope you enjoyed the mini lecture series. For those who've been watching along, I realized at the end, as is always the case with any teacher, any educator, that you can always improve upon your lessons, but I really hope that it's opened, broadened your horizons, and you've learned a lot more about the world, especially the quantum world. And for me, it's really just about sharing my knowledge and hopefully inspiring others. So I hope you've enjoyed the journey.